In this video we show how to use the non-parametric statistical technique called empirical likelihood. The data is the same as before, so it's the student scores in two different classes. And so the traditional way of analyzing this kind of data would, for instance, be to construct the confidence intervals for all averages, which we could do like this. But these confidence intervals are created under the assumption that, that the distributions being used to approximate the data are actually Gaussian distributions with equal standard deviation. So confidence intervals are constructed within this class of distributions. Now there's a new technique which doesn't assume any parametric class of distributions such as Gaussian distributions, but actually optimizes over all possible distributions. This technique is called empirical likelihood. So what you could do is, for instance, for all the averages, create confidence intervals. So if we can, and we can actually compare, because we can, on the left we can put the condition versus the average. So here you have the confidence intervals according to the traditional parametric technique using Gaussian distributions, and here you have the same result using empirical likelihood. So notice that the differences are actually, in this case, quite small, because Gaussian distributions are actually a fair model for the data. One of the advantages of empirical likelihood is that you can also make what is called a robust estimate, which means that you use a statistic which is much more insensitive than Gaussian statistics for outliers, so values that differ more than 3 standard deviations from the average. So there's some parameters for this empirical likelihood, so there's a number of options that you could choose. So we chose one of these options, and we create the empirical likelihood. So we see again very little difference with what we found before, and also very little difference with the parametric results. Just showing that there are no extreme outliers. So in this case, it shows that parametric techniques actually work fairly well. We can also look at the estimate for the difference, for instance, between either in a robust or a non-robust way. Let's directly take the robust estimate, and we see that according to empirical likelihood, 0 is within the confidence interval, so there's no significant difference between both conditions. So let's put that one here, and let's create a similar result for the parametric estimates, and we'll see that again both results are pretty close together. Other things we can do with empirical likelihood is we can also create estimates for higher order moments. For instance, we can create empirical likelihood estimates for the standard deviations. So we see that the estimated standard deviation is about the same in both conditions, and this is one way of looking at it, but we can also do this comparison directly. We can actually look at the ratio of 2 standard deviations and create an interval for that, and we see that 1, which is within that interval. Note that this is generalization for a well-known test in traditional statistics, which is called the F-test, but again the F-test only works for Gaussian distributions. This could work for any kind of distribution, and it would also work if the data are not continuous but discrete. You can even look at even higher order estimates, like the skewness. The skewness is a measure for how symmetric a distribution, or in this case a histogram, is. And a symmetric distribution would have a skewness of 0, And so we see that in neither of the two conditions there's actually significant difference from a symmetric distribution, although obviously there's some more hints of asymmetry in the first condition and in the second condition. The fourth order moment is called the kurtosis. You can also create that one. And the kurtosis of a Gaussian distribution is equal to 3. So the first case, the width of the distribution is similar to what we expect of a Gaussian. In the second condition, 3 is just on the boundary of the significance interval, so it's marginally different from a Gaussian. It means the value is smaller than 3, that the distribution is actually a little bit more peaked than a Gaussian distribution.